while René sets up his microphone, I can introduce him and his co-authors. Please bring them back on the slide. Thanks. So the next talk will be given by René Thiemann, and it's joint work with now Hirokawa, Dohan Kim, Kiraku Shintani. And we are switching a topic again quite drastically. This time it's about proving confluence and commutation in rewriting via parallel critical pairs.
Okay,
Please
thanks for the introduction. Yes, so I will actually start with explaining the title, which is quite longish, and I will go word for word through this title. So let's first speak about certification. What is my view on certification? That I actually consider that there are analysis tools which are unverified, highly optimized, which somehow produce answers which we then want to swallow, and hopefully they are correct, like an SMT solver, a termination analysis tool, or a confluence analysis tool, a SAT solver, whatsoever, right? So what we basically have is we have this part here where this tool just eats some formula or program as input and then says, well, this is the answer to this problem, and gives us some certificate, so some proof or some reason why this should be the correct answer. Okay, and under certification, I understand the following, that we don't trust these unverified tools blindly, but we actually want to certify that indeed the certificate that is given here is a valid reason for the answer. For that, we somehow take a detour. We first look at the algorithms that are used here and formalize them in a proof assistance, and also check whether these algorithms and techniques have been applied correctly. So the certifier is an easier program because it doesn't have to do the proof search, but it still has to come with a verified algorithms. And this is what I call the certifier. This is certification in this context here in this talk. Okay, and then once the certifier accepts a proof, we have a high assurance that indeed the answer is correct. And in my particular application, the proof assistance that I'm using is Isabelle HOL, and the certifier that I want to talk about is the CETA certifier. Good. So the aim of this talk is now to extend the power of this existing certifier. So this is certification. Next up is confluence and commutation. What is confluence? Confluence is a very abstract property. Basically, it says that whenever we have some computation going on, and this might be non-deterministic, then we might have the situation that we have a starting point from which we want to compute, and there are two ways to compute it. We can either go the left path to some intermediate state t, or to some term u here. And then confluence says, no matter how these initial computations work, we can always join these computations. Okay, so this is confluence, and that is a desirable property of, many programs, which we would like to certify that it holds. Unfortunately, it's undecidable for most programming languages. Commutation, on the other hand, is a generalization of confluence where we now have two systems. So we have, say, the original program in black and an optimized program in red, and then we want to relate these programs that they are equivalent, so to say, that they can simulate each other. And of course, if we choose red and black to be the same, then we end up with confluence, so the previous notion. So both of these properties are undecidable, and both of these properties are tested, for instance, in the annual confluence competition, where several tools try on a database of confluence and commutation problems to prove or disprove as many problems as possible in an unreliable way, right? Good. So this is the second part of the title. Now for the last part, parallel critical pairs. So for confluence, we basically have the situation that no matter how many steps we do, we try to find some join here. This is something which is actually very hard to analyze because having arbitrary many steps here is something which is hard to capture syntactically or somehow. Therefore, a much more desirable analysis is local confluence, where we just do a single step to each side. Okay, so this is easier to see what is going on there. And then in the context of term rewriting or functional programs, this can be captured by a so-called critical pair, such a local peak. So there is a syntactic criterion which tells us, well, these are all the bad situations that can arise where these potential non-determinism can lead to different results. So this is nice, but it is of limited power because the property we are interested in is really full confluence, and there is Newman's lemma, which tells us that provided we have termination, the two notions are equivalent. But termination is somehow a hard restriction. And the confluence competition usually is not interested in those things which are terminating because then it's trivial, because then it's decidable. Okay, so we are interested in the non-terminating confluence analysis. And to get rid of this termination assumption, we consider local peaks not of the original rewrite relation, but of the one with parallel rewriting. So we do overlaps, local overlaps of parallel computation steps, and therefore we get less restrictions. And these one-step overlaps of the parallel rewrite steps, this is exactly what the parallel critical pairs can capture. So this is parallel critical pairs. Now let's put this together. Let's do confluence proving via parallel critical pairs. Why is this of interest? Because what you see here is a history of various different techniques for proving confluence of different power. And you see here that actually the red box outside here of the work of Shintani and Hirokawa, they proved that by using parallel critical pairs, they can simulate all of these inner other confluence criteria. Some of them are also relying on parallel critical pairs, but even those which rely upon ordinary critical pairs in the non-parallel setting. So it's really quite a powerful technique, so it's worthwhile to formalize this part in a theorem prover. Moreover, for the competition, where we want to try to support validate as many proofs as possible, there are certain tools which know that, well, parallel critical pairs are among the most powerful tools. They only produce proofs that use these PCP-based techniques. So for instance, Haxan is a tool where all proofs are used by PCPs, and we cannot validate a single proof of Haxan prior to this work. Okay, so this is the situation. The situation is even worse because before this work, there was no formalization even of the definition of parallel critical pairs that I'm aware of, so we really had to start from scratch there. We could use the unification algorithm that we have, but that's it, basically. And what we do here is we really formalize the red marked parallel critical pair-based confluence techniques and generalized all of them to commutation. Why the red ones? Well, basically Gramlich one is the simplest one, so this is somehow, well, the low-hanging fruit that we needed to get started with, to get familiar with all the reasoning that is done with before we go to the more complex one and finally the most powerful ones, which most likely are more difficult. So do it in a stepwise fashion. What we did not formalize is all of these subsumption relations. So we really just proved soundness as confluence criteria, but not the diagram itself. Good, so let's give you a little bit more details on parallel critical pairs. As I said, this is an extension of a standard critical pair, and it's used to capture the all the possible overlaps of two parallel rewrite steps. So how does this work? Assume we have a rewrite system like this, or think of it as a functional program if you want, where we have two left-hand sides here, which rewrite to two right-hand sides, where the right-hand sides at this moment do not matter. Then you can see, if I now consider the left-hand side of the first rule, and I plug in for the x here at this point a 0, then clearly I can either use the left-hand side goes to right-hand side 1, or I can reduce the subterm times 0 something to the right-hand side. So this is a standard critical pair. And we see an overlap here, we see an overlap here, and for parallel critical pairs, I also consider the overlap which is done in parallel. So both of these overlaps occur. So I get 3 critical parallel pairs in this example instead of just 2 in the ordinary case. So this is the rough idea of what is going on in parallel critical pairs. So let us look at formalizing this. Of course, we had a look at the literature. How is this defined? You can find this in Tobias and Franz Bader's textbook, or you can find it in the original papers, and all of them have a formulation that is similar to what you see now on the slide that is upcoming. Namely, we start with a rewrite system and pick one specific rule out of this system and want to compute the overlaps with the left-hand side of this rule L0 to R0. To that end, we now consider an arbitrary non-empty set of positions of this term L0, where these positions are all pairwise orthogonal. So independent positions of the term L0, which point to non-variable subterms. And now we select the other rules where we want to do the overlap with these subterms. So we pick rules Li to Ri from R, all of them, and we have to rename the variables. So that unification somehow can consider that each rule is applied independently. Now we do unification. So we unify the left-hand sides here, the Li's, with the subterms of the L0 left-hand sides. And then we can somehow define what is the term where the divergence may happen. Namely, this is the term S, which is either L0 sigma, where we then can reduce to R0 sigma. But due to unification, this is the same as the L0 sigma term where we plug in the Li sigma subterms, and then we can rewrite in parallel to the right-hand sides, Ri sigma. Okay, and this is then a parallel critical peak, and the corresponding left and right term is then the parallel critical pair. And this basically captures the possible divergence of a single parallel overlap, local overlap. And now all of these criteria somehow differ in how these parallel critical peaks or pairs have to be merged. So there are certain conditions, rules might be labeled, etc. But the general idea is all via we can simulate a local peak by this. Good. So this is the definition, and let's make it formal, right? Formal in the sense of going to a theorem prover. And here we actually hit several problems, right? First one, each position of Pi must be a valid position. So it must be a position of L0. So yeah, okay, we can deal with that. Well, the positions are pairwise orthogonal. Yes, we can define that, but we somehow have to ensure that, right? We have to take an arbitrary variable renaming. Okay, there are infinitely many. Which should we take, right? Not so nice. And we have to do parallel replacement. Oh, parallel replacement is also an interesting operation. How do we define that? Do we do it stepwise, one position after the other, or do we do it by induction over structural recursion over the term? So not so obvious how to define this at all. And once we have this, how do we get an algorithm which actually computes us the set of parallel critical pairs? So all of this needs to be set up, and we initially tried to do this literally as it was defined, and it was a mess, and it was no fun, and we abolished this definition. So our solution, therefore, really is forget about this definition, forget this, so it's not a good definition. So switch to a better one, and here it comes. So the first one is, what we did is we don't want to do this reasoning about variable renaming in the definition of critical pairs itself, but we do it inside the unification algorithm so that we have a specialized unification algorithm, which once and for all treats this problem of renaming. Moreover, we don't use anymore position-based reasoning, but we use contexts. So context, I will show you a few slides in a minute, and it will get rid of many of the side conditions. So there is only minimal side conditions that we have to care about. And moreover, it can be shown that by this definition, one can also define a very natural, structural, recursively defined algorithm to compute critical pairs. So it's simple. Good. So let's start. Have a look at the different tasks. The first one is unification with renaming. So as I said, we want to do renaming integrated into the unification algorithm. And so we don't have to do the reasoning later on when reasoning about critical pairs. So what is the design of our algorithm? We call it MGRen for most general unifier with renaming. And it either delivers a set of substitutions, not a single substitution, or bottom to indicate it's not unifiable. And what we do is, in our application, we need to instantiate each left-hand side we want to plug in with some unifier. So we get many substitutions sigma I for each subterm, so to say. And on the other hand, we have this L0 left-hand side where we always have to pick the same substitution. So therefore, it becomes asymmetric. So we have many substitutions for one ingredient, only one substitution tau on the other side. And these are the properties, namely, if we plug in a unification problem here, and the result is not bottom, it will return a list sigma 1 to sigma n tau. Then indeed we get a unifier in the sense that Si sigma is the same as Ti tau. Okay, so we plug in the different substitutions on the left and the same substitution on the right. And we also have a completeness result stating that, well, the other way around, if we have a unifier, then the unification algorithm will deliver primed version of it, and these primed versions are actually more general than the original substitution because we can add a substitution gamma and then get back the original substitution. Okay, so as is in a unification algorithm. How did we implement that? That was actually quite easy. We just invoke a standard unification algorithm, a verified one, where we then, before doing the unification, we rename all the variables in Si by yi underscore, where y and underscore are really literal strings, and I is here the string I, and the Ti is renamed by x. Okay? I was told that actually, after I showed this to some of the tool developers, that actually he did that also, but he didn't use the underscore, and if you forgot the underscore, then it's wrong. So then you have a clash. So the underscore really is important. Good. How does this look like in Isabelle? Basically, the soundness is as expected. So, well, if the unification algorithm returns a list of substitutions mu and tau, then you get a unifier, right? And the length matches. However, the completeness result looks more tedious. Here it is. basically, you can forget about these lines and about these lines. This is what you actually would expect. So if you have a unification problem that's solvable, then the unification algorithm returns something which is more general. This is exactly what you expect, but it turns out that this is not enough for actually verifying later on the critical pair criteria. You need more properties out of it. So initially we just had that, but you need also something else, namely you need to know how the unifiers work on the variables outside that do not occur in the unification problem. That there, these variables basically can only be mapped to variables and that this function is injective. And, well, it actually has to be outside a further technical restricted set of variables. Okay, so this is the result for the unification part. Now let's move on to the definition of parallel critical pairs via context. I will briefly introduce context. A context is just a term with a hole where you can plug in a term later on. So a context can have many holes, and we write the number of holes with this hash h. And then we write CT1 to Tn for plugging in the terms into a context. And then the only assumption that we need for such a context is that if we plug something into a context, the number of holes matches the number of terms. So we disallow that we have too few or too many holes. But this is a very simple minor side condition. And then the advantage of using this context is that many things can be described quite naturally. For instance, the parallel rewrite relation here can be described without just with the context and without any inductive definition. So in one line by doing a parallel replacement within a context here. And now we also can describe the parallel critical pairs via context. So we pick some arbitrary TRS and a rule as before. And now we choose an arbitrary decomposition into a left-hand side into a context with subterms. We assume that the number of holes is non-empty because we need to have at least one overlap. We pick arbitrary rules, no variable renaming required. And now we just invoke our unification algorithm and extract the substitution, define the terms, and get the corresponding critical parallel critical pairs and peaks. So in this definition, there is no treatment of positions required, no orthogonality. It's all implicitly in the context, right? And since this is in sync with the rewrite relation, basically we can do easy structural reduction over context to then prove properties. Okay, for time reasons, I just tell you that with this definition you can also easily define an algorithm which computes all these decompositions which are required here. And then we go to the key lemma. And the key lemma basically states that local parallel peaks can be simulated by a parallel critical pair. And this is the key lemma and was the most tedious lemma of all of this development. The problem is that we wanted to have this key lemma and reuse it for all of the other confluence techniques. So we had to make it as strong that all of the additional properties that are used by all of these techniques are available in one go, and that is general enough to capture the reasoning in one go. And this is 400 lines without induction proof for just this key lemma, reasoning about the renamings, etc., about the variables. That was really, well, no fun, and you don't find it in any textbook, the reasoning that is required. There it's always, oh, passt schon. Yeah. So, in comparison, the 1,800 lines for the complicated techniques in the papers, that was easy going. You could just follow the structure of the original proofs, but these 400 lines were a mess, so hard. So here's the key lemma in Isabelle, and you see, well, there are quite some properties here, additional properties, and be sure that each of these properties was only added because some of the Confluence techniques required them. Good. So after having the key lemma, progress was very quick, and we could just rush through all of the results, get them. We added certificate checking algorithms to CETA, so verified algorithms which can compute this, and we also added certificate generation to Haxan. And as a result now, for the Confluence competition, where there are 233 hopefully Confluence systems, at least the unverified tools say so. Previously, 159 could be certified. Now we could add 20 more, right? And moreover, due to the benefits of formalization, we could easily then generalize all of it to commutation by just saying, well, we consider 2 rewrite systems, and the Isabelle pointed us to those places where we had to adjust, and all of these adjustments actually were harmless, so were easy to fix. So to summarize, well, we have formalized all this and can now check Confluence proofs like this with parallel critical pairs, and here you see one of the new proofs, and you don't want to check it by hand or trust a human on this. Thanks.
Thanks, René. Do we have questions?
It's very slightly outside of the topic of the talk, and I'm not very privy to competition in Confluence checking, but I know that in communities it can be quite difficult to get different people to agree on some input and output formats. Do you have any hope? Are you trying to convince people to get their tool to output certificates that can be checked by your certifier?
Yes, actually, it is already the case. So CETA is used for the termination competition and for the Confluence competition. And there was agreement upon the existing certifier to impose some format on the community of termination tools that they agreed to.
Great.
And yes, in the meantime, there is now, for the Confluence competition, there are 2 competing formats. There is the one format that is also supported by CETA, and there is a different format for a special tool, another certifier, which works completely differently, and somehow the tools can choose between either CETA format or the other one. And many tools actually support it because, well, we detected over the years several bugs in several tools, and actually they know what they get when they add certificates. So the competition are rather harsh. So if there is a conflict, so one tool says yes, the other says no, then one of them will be disqualified. So they better want to check upfront whether they are sound.
Thanks.
Hi. I was kind of wondering, these kind of Confluence proofs, they're very tedious to do in proof assistance when we have like our favorite new language or something with a bunch of rewrite rules, and it's kind of annoying to prove by hand every time that we have some Confluence properties. And I was wondering kind of naively whether this kind of things can be used, say I want to formalize in Isabelle, my new shiny language. Could I try and use some of the things that you've developed here to kind of generate the Confluence proofs for me and not have to do it myself by hand at nth time, because it's not that interesting?
You mean you want to get Confluence tools for some other proof assistance done? Or?
So what I mean is that kind of using the kind of Confluence checking algorithm that you've certified here, to basically obtain certificates that I can use when like doing like PL work, say, and I need some Confluence lemma for a given rewriting system, basically in my proof assistant.
In your proof assistant will be difficult because I wouldn't know how to export the thing that we check. I mean, in the end, in our workflow, what we get is we do code generation.
Yeah, okay.
Right? And therefore, we just get an executable where we know that it's sound, but this doesn't export a proof into another proof system or something. So no proof objects are created.
Okay, thank you.
All right, I think it's time for the break. So let's thank René again and